Today we'll be talking about distributed data parallel programming. In previous lectures, Professor Victor Kunchak and Dr. Alex Prokopech have gone through different sorts of parallelism. We've touched on task parallelism and data parallelism, and always when we've been working with different sorts of parallelism, we've been more or less focused on one machine. Today, we're going to extend that notion to the distributed case, the case where we're programming between many possible computers. So far, we've seen data parallelism on a single multi-core, multi-processor machine, and as Dr. Alex Prokopech has shown, parallel collections is an implementation of this paradigm in Scala. So the idea, if you remember, is that parallel collections look a lot like regular Scala collections. It's just that the operations that you do on them are executed in parallel. And Alex had gone through and taught you a little bit about how different sorts of operations are done. We're going to extend that now to the distributed case. So data parallelism, today we're going to talk about data parallelism in a distributed setting. And in particular, we're going to focus on a very popular distributed collections abstraction called Spark, or Apache Spark, as an implementation of this paradigm. So whereas parallel collections in Scala implemented this paradigm in the single machine scenario, Spark implements this paradigm in the distributed scenario. So first, what do we mean by distribution? Distribution introduces important concerns beyond what we've had to worry about when dealing with parallelism in the shared memory case. All sorts of things can happen in the distributed case that we didn't necessarily find ourselves concerned about in previous lectures. One example is partial failure. So the sort of failure where something where there's some sort of failure in a one or more machines involved in a distributed computation. Okay, so we have the basic idea that distribution. So I'm pretty sure. Okay, I'm sure that we have the basic idea of what distribution means, or the distributed case is. It's the situation. It's the case where you have many machines where you're trying to coordinate some sort of data parallel computation between these machines. However, that's not the only story. So first, let's talk about what we even mean by distribution and sort of what's important to consider in the distributed case. So first of all, I think we can all kind of agree that distribution means doing, in this case, a data parallel. So, I think we can all agree that I think we're more or less all on the same page about the basic definition of distribution. Distribution means, in this case, in the data parallel case, coordinating a data parallel computation over more than one machine in multiple address spaces. However, when we move to this case, distribution introduces important concerns beyond what we had to worry about when dealing with the shared memory case. Two examples include the notion of partial failure. What happens in the case that one of the machines, or one of the distributed workers, crashes or somehow doesn't complete or takes much longer than other machines? What can we do about that? That's not something we've considered so far. And further, what happens when there's traffic on the network, when there's much more latency than expected due to other network communication? Because, after all, we have to be sending messages back and forth, be sharing data between different computers on a network. Partial failure and latency are two central concerns to distributed computation that we will explore in a little bit more detail. And one important thing which I wish to show you throughout these lectures is that you're always going to have to remember, as a programmer using a framework like Apache Spark, that latency cannot be masked completely. It will actually even be an important aspect that impacts the programming model as well. So you can never forget when you're programming with Apache Spark that cannot and will not be masked completely in the Spark scenario. It'll always be an important aspect that impacts the programming model. So it'll even come out when you're writing code, having to think about when communication will occur and when to kick that communication off. I'll show you in just a moment what I mean. But first, let's get a little bit of intuition about how important latency is. Why do we even care about latency? There's been a cool little chart that many people in open source have all contributed to. It originated with Peter Norvig, and several others have added to it in different ways. I include a link down here to a GitHub gist that collects a lot of the information. If you're interested to see it, it's there's much more information than included on the slides. However, first let's just get a little bit of a sense about what latency even means. This is a very helpful chart that lets you empirically about how much time it takes to do different sorts of operations. So on this first page here, you can see that an L1 cache reference is only half of a nanosecond. Referencing the main memory, significantly more expensive, but still only around 100 nanoseconds. Sending 2 kilobytes over a 1 gigabyte per second network, around 20 microseconds. An SSD random read, so an SSD drive, a random read on that drive is about 150 microseconds. And if we move up to sending data around within the same data center, or even sending a packet round trip over the Atlantic Ocean and back, we can see sort of the order of magnitude differences. So in this case, doing a round trip within the same data center, this is only half of a millisecond, but sending a packet from California to the Netherlands back to California, that's about 150 milliseconds. So we can see the general trend here is that as we move data farther distances, certainly the amount of time that it takes drastically increases, often, many orders of magnitude. But these are all just different orders of magnitude. We're adding zeros here, but it's really difficult from these numbers to grab any sort of intuition. I see that it's several orders of magnitude. Takes several orders of magnitude more time to send a packet to California to the Netherlands and back to California again when you compare that to an L1 cache reference or a reference to main memory. But this is all still relatively fast. 100 nanoseconds, 150 milliseconds. I can't really feel the difference as a human being. I can try to visualize this, where one little black block here equals 1 nanosecond. One blue block equals 100 nanoseconds. One green block equals 10 microseconds. And one red block equals 1 millisecond. So I can try to combine all of these sort of things visually to try and get a feeling for how expensive different things are. So the difference, for example, between an L1 cache reference and a mutex lock-unlock, we can kind of visualize this here. So it's half of a nanosecond versus 25 nanoseconds. So while we can visualize this a little bit, it's still a little bit difficult to get some intuition for how expensive this is compared to how expensive that is. All I can really get from this graph is that, well, this is much cheaper than that, for example. But how much cheaper? How much cheaper really? So Eric Meyer, a professor at TU Delft, had the great idea to humanize these durations. So the idea is take all of these durations and multiply them by 1 billion. Then we can map each latency number to some sort of human activity. So if we multiply this L1 cache reference duration by 1 billion, that's about half a second. That's about half a second, around a heartbeat, more or less. A mutex lock and unlock, in this case, about 25 seconds. So the difference is 1 heartbeat versus, making a coffee in one of these nice little coffee machines. A main memory reference, in that case, is about 100 seconds. So that the difference between a L1 cache reference and a main memory reference is like the difference between 1 heartbeat and brushing your teeth. Okay, let's continue. That doesn't sound so bad. If we send 2 kilobytes over 1 gigabyte network, that takes about 5.5 hours. So that's, if you, again, try to map this to a human day, that's about the time it takes from lunch to the end of a work day. An SSS random read, about 1.7 days, which is around the length of a normal weekend. reading 1 megabyte sequentially from SSD. That's 11.6 days, which is about waiting almost 2 weeks for a delivery. So this is we can start to feel a difference here about how much each one of these sorts of operation takes relative to one another. It's actually quite a big difference when we map it to our own selves, right? Well, what's most interesting is when we start getting up to sending data back and forth over long distances. So if we want to come back to this example of sending a packet from California to the Netherlands and back to California again, the relative duration to an L1 cache reference is about 1 heartbeat to 4.8 years. So about the average time it takes to complete a bachelor's degree in places like the U.S. So what I hope you carry away from these humanized latency numbers, so to say, is that there is really quite a big difference between trying to keep stuff in memory and operate on things in memory and making network making requests and sending things over the network. It's actually quite expensive in a relative sense to do computations that require a lot of network communication. So if we're going to come back to this example of distributed data parallel programming, we're going to want to try and keep things in memory as much as possible and to reduce as much network communication as possible, if we've gathered any intuition from these humanized latency numbers that I've shown you here. So now that we have a little bit of a sense about how long it takes to send stuff over the wire versus how long it takes to operate on it in memory, and we know that we'd like to try and keep our computations on one machine and do as little communication as possible to reduce the amount of time we're sending data over the network. What is the macroscopic view of doing one of these sort of distributed data parallel computations look like? So if we start with our shared memory view of the world and we have one machine, one address space, and in this case, we have some set of data. You can imagine, like in the parallel collections case, we have this is something like an array. And in the parallel collections case, the way that we operate on this piece of data in memory is we break it into pieces, and we process each individual piece. So the basic idea is that you're breaking this collection up into pieces, and you're working on different sized chunks in some way. In the case of parallel collections, parallel collections under the hood uses the fork join pool to operate on each individual piece, which is, you can think of it like threads working on individual pieces, right? So that's the shared memory case. What does the distributed case look like? Well, kind of the same idea, but rather than individual worker threads, if you want to visualize this, you have individual pieces of data on different machines, and instead you're worrying about the communication that happens between the individual machines. So in the shared memory case, the programmer uses the same data parallel program model, the same interface that they've been using, that we've seen in earlier, but in this case, the data is partitioned in memory and operated in parallel in the same memory space. However, in the distributed case, we still have the same interface, the same data parallel programming model that the programmer interacts with, except in this case, data is partitioned between machines with the network in between, and all of these pieces of data are also operated on in parallel. Since we're still talking about the same programming model, but realized in different sorts of environments, all of the properties that we learned earlier related to the shared memory case, such as in parallel collections, can still be applied to the distributed counterparts. So for example, even in the distributed case, you want to watch out for non-associative reduction operations. But now we must also consider latency when using our model, or situations that could introduce latency, and we'll see a little bit more about what that means shortly. So as alluded to earlier, we're going to focus on Apache Spark. Apache Spark is a framework for distributed data parallel programming. It's very, very popular in industry at the moment. Lots of big companies are using this to do big data analytics and even things like machine learning on very large data sets. And what's important to note, even for regular day-to-day programmers with Spark implements a distributed data parallel model, which is called Resilient Distributed Datasets. That's the name of the model that was originally implemented. And this is how it was named in a research paper, but this is actually what we refer to Spark collections as. They're called RDDs. So throughout the rest of the course, we're going to be talking about Spark and RDDs. And RDDs are the distributed data that we operate on. So they can be thought of as like a distributed array or a distributed sort of list abstraction. For this and the next two lectures, the best book to reference, if you need any sort of learning material, would be the Learning Spark book by Holden Karau, Andy Konwinski, Patrick Wendell, and Matej Zaharia. These folks all work on Spark. Matej Zaharia is the original author of Spark. So this is a great book. It's a great resource from the creators of Spark. So let's drill a little bit more into these resilient distributed datasets, these RDDs. What are they? RDDs look just like immutable sequential or parallel Scala collections. So if you remember, on Scala parallel and sequential collections, you have a handful of combinators. You have a handful of operations that you can usually use, right? So you have a map, flat map, filter, reduce, fold, aggregate. So does RDDs. RDDs have map, flat map, filter, reduce, fold, and aggregate, and they all mean the same in the Spark universe as they do in the parallel and sequential collections universe. In both cases, all of these combinators do semantically the same thing. A map will go through all of the elements in the collection and apply a function and return a new collection, for example. The same is true in the case for list as it is for the case of RDDs. Here are a few example signatures which illustrate what I mean. So as you can see here, this is an example of what the signature on list can be thought of as. But the idea is still the same. Map takes a function from some type A to another type B. So, and it returns a new list of type B. The same is true for the RDD case. So it applies so in both cases, the map. So let's have a look at some of the signatures of these methods that are both on Scala collections and also on Spark RDDs. As you can see, map takes a function, the same as list does in Scala collections, but instead of returning, of course, a list, it returns an RDD. So the map function on RDDs return an RDDs, just like the map function on lists return a list, right? This is true for most other operations, reduce, fold, and as we saw in the previous slide, flat map and filter as well. However, there is a little bit of a difference with this aggregate function here. If you recall from the earlier section of the course when we covered parallel collections, you'll recall that this aggregate function is effectively a general version of fold left that enables things to be operated or aggregated or folded in parallel. The idea is that it splits the collection or the iterator into partitions, and then it processes each partition by sequentially applying this seek up function. And it starts with this 0, this z here, just like in fold left. And finally, everything is combined with this comb up. So what this basically does is it splits the collection into a number of pieces, and it computes partial results using the computation function, and then it combines all of these results using the combination function. This enables these folds to happen in parallel. However, there's one crucial difference between the Scala version and the Spark version. There's a by-name parameter here. Do you have any idea why that could be? A hint is that the aggregate method in the Scala parallel collections case is potentially executing in parallel in the same memory space. I'm going to leave this as a little thought exercise, but it's actually kind of an important exercise for you to try and mentally walk through on your own. The idea is to remember that in one case we're happening in the same memory space, and in the other case we're happening between machines, effectively. So why do you think this could matter, that this 0 is a by-name parameter? We'll discuss this in the exercise session next time. So by now, I hope I've convinced you that RDDs in Spark, they actually look and feel a lot like normal sequential or parallel collections in Scala. The only thing is that you have to kind of always remember that your data isn't sitting on one machine, that it could be potentially distributed across many. So to get a better feeling of what that means, why you have to think about it, let's look at a little example. Let's say we have a VAL encyclopedia that is a distributed collection, an RDD, that's full of strings. And let's just say that each one of these strings represents a page, like a page of Wikipedia. And we want to search this encyclopedia for all mentions of EPFL and count the number of pages that mention EPFL. So pretend that encyclopedia is actually an RDD of Wikipedia pages. So recalling Scala parallel and sequential collections, it's a pretty simple to try and find all of the pages that contain the string EPFL. We have a collection of strings. We just call filter on this collection of strings, and for each page, for each string in this collection, which represents a page, we check to see if that page contains the substring EPFL. We get a collection of all of the pages that do, and then we sum them up. Let's look at another quick example. This is the hello world of programming with Spark. So let's say we'd like to do word count. This is if you look at Hadoop tutorials or anything in this big data space, word count is the hello world example. So how easy is it in Spark? Well, we start by creating an RDD. There's a lot of ways to create an RDD in Spark, but perhaps the simplest way is to start with this thing called a Spark context. We'll see later where that comes from, and we just instruct it to read from a text file. In this case, some text file in HDFS, which is a distributed file system. And how now might one just with your knowledge of regular Scala collections, if again I have a big RDD full of strings, how do I count the words in those strings? Just again, remember sequential Scala collections. How would that be potentially possible? Well, it's pretty simple if you think about Scala collections and lists or parallel collections, right? You can just call a flat map on your RDD, and for each line, break everything up into words by splitting on spaces, and then just map each word to a pair of word and one. And we can just do reduce by key. So we can reduce we can sum up all of the ones in these pairs. That's it. So here we have only a few lines we can do word count on an entire Wikipedia collection of Wikipedia articles, for example. Pretty simple, right? Spark also feels a lot like Scala collections when it comes to this notion of transformations and actions. If you recall from Scala collections, we have this notion of transformers and accessors. Some similarity there, right, between transformations and transformers and actions and accessors, right? Still the same sort of idea in Spark. So let's start with transformers that we remember from Scala collections. So the idea is that we call this method, this transformation method, this transformer method, and they always return new collections as results. So examples are map, filter, flat map, group by. In all of these cases, we're calling a method map on something like a list, and we're getting back another list. So we don't get back a single value, we get back another collection. Those are transformers in regular Scala collections. And then there exists something called accessors. So accessors is kind of the opposite. Rather than returning entire collections, we return single values as results. So examples include reduce, fold, or aggregate. We will go through an entire collection and we'll return a single value. Similarly, in Spark, we have transformations and actions. Just like in Scala collections, transformations return new RDDs as results, and actions are just like accessors, where they compute a single result based on some RDD, and they either return that result or save it to some sort of external storage system like HDFS. However, there is one crucial difference. I'm going to draw lots of exclamation points here, because this is one thing you're going to have to remember throughout the rest of the course. Transformations, unlike Scala collections, are always lazy, and actions are always eager. That means that when you call a transformation, you don't immediately compute the result. So when you call a map, for example, on a Spark RDD, the map function isn't applied to that RDD yet. It's just queued up for computation. You have to eventually instruct the cluster to begin that computation. So transformations are always deferred. They're not begun when you call the method map on your RDD. Actions, on the other hand, are eager. The result is immediately computed. So if you call, for example, a map and then a reduce, the map and the reduce will be kicked off. And an important takeaway here is that laziness, eagerness, these two ideas is how we can limit the network communication when using the programming model. So remember how expensive latency can be when you're sending data around. It could be many orders of magnitude slower than operating in memory. Having lazy transformations and eager actions gives the programmer a handle on when network communication is occurring. So let me illustrate what I mean. So let's create a new RDD, and let's call map on it. First off, I'm showing you a new way to create a new RDD. This parallelized method will take something like a regular list, so a list of string, and it will create a new RDD of strings from that Scala collection. Again, this SC thing is a Spark context. We'll talk about that in a little bit, but you use this Spark context to create RDDs. We take our RDD of words, and we call map on it. Now what's happened? What's going on in the cluster? Well, the answer is nothing. As alluded to on the previous slide, the execution of map is deferred. It's a transformation. So nothing has happened. We've just queued up that this computation should eventually be done. However, we can add an action. Reduce is an action. It returns a single value. We can sum up all of these lengths, and everything starts. The computation begins. But aha, there's a new question. If you perform an action on an RDD, on what machine is its result returned to? So for example, if I have an RDD full of person objects, and if I say take 10 on this, because take 10 is an action, it should return a subset of the full RDD as some other collection back, right? So where will this array of person objects be if I call this function? Take is an action. Take returns an array of person, and it returns it somewhere. But where does it return it to? Where does this new subset, this new smaller data structure, where does it end up if the larger data structure is on potentially hundreds of nodes? Well, first we have to look at how Spark programs are executed. Here's a little diagram of how Spark programs are organized. The two main points are that there exists something called a driver program and something called worker nodes, or programs that should be executing on workers. When you're programming, you as the programmer, you're living in this world of this driver program. So when you call map, when you call reduce, this guy is doing that work and sending it to each of the workers and telling the workers to do that task and return results. So if you call reduce on this, from this driver program, basically what should happen is that the maps and whatever else that are done would be coordinated and done on these worker nodes, and eventually the result is sent back over the network to the driver program. So the driver program runs the Spark application, which creates this Spark context. The Spark context is your handle to Spark. The Spark context then connects to this thing called the cluster manager and figures out how to access all of these workers. And on each worker node, there exists this thing called an executor. Executors are the processes that run all of the computations and store all of the data for your application. So once all of this is set up, the driver program, through the cluster manager, sends its instructions to the worker nodes, and results are returned to the driver program when actions are used. So back to this question. So if I perform an action on an RDD, on what machine is its result returned to? Well, since now we have some idea of this driver program existing, the result will be returned to the driver program. So in general, when you execute an action, it involves communication between worker nodes and the node running the driver program. So the result is computed and sent right back to this driver program. So the general idea that Spark computes RDDs the first time that they are used in an action actually helps when processing large amounts of data. To back that statement up, let's look at a quick little example. So let's say we have a very large data set of logs, and they're all stored as strings in an RDD. We can look at all of the logs that occurred in the last year, which contains the message error. Let's just say we're only interested in looking at the errors that occurred in some running system that ran for a long time. And let's say, okay, let's just take 10 of those errors and look at them. This sort of lazy evaluation approach enables all sorts of optimizations to happen. In this case, Spark first analyzes the sort of chain of operations before executing them. Spark, in this case, doesn't have to compute intermediate RDDs. Instead, as soon as the 10 elements of this take method have been computed, first logs with errors is done. We don't have to go through all of the hundreds of other potential shards of this data set. At this point, Spark can stop working, it can save time and space, not having to compute the elements of the unused result, a filter. This sort of delayed execution allows Spark to analyze chains of operations and do optimizations like these, which can be very beneficial on very large data sets, for example. Spark can also save effort by caching data. So by default, RDDs are recomputed each time you run an action on them. So for example, each time you run take, everything is run again and again and again. This can be expensive, especially in time, if you need to traverse a data set several times. This is actually quite common. You might want to take a very large data set, filter it down, and then use that filtered down sort of subset of the big data set to do many other different sorts of operations on it. So maybe you want to, in different ways, analyze that collection of error logs from the first example, but you don't want to go through the entire collection and recompute this filter bit again and again and again, right? So Spark allows something called caching and also persistence to allow control over what you keep in memory so you can revisit it many times if needed. So if we go back to this example of trying to filter out just the error logs computed in the last year in some large data set, we can use this persist method to signal to Spark to say, hey, I'm probably going to reuse this logs with errors again. So keep that in memory, because maybe I might just call take now, but perhaps a few lines later I might need this again to do some other thing. So maybe I would like to try and find a certain kind of error messages. So maybe I'd like to call filter and take yet again to make a smaller subset. But I don't want to have to recompute this whole logs with errors twice. I want to use it just once. I want to keep it in memory and then use it several times. So this persist function caches this logs with errors thing in memory. So now if I want to do something else, if I want to now count all of the logs with errors, this is much faster. If I did not persist this, I would compute logs with errors twice. I would compute it once here, and then again here, if this persist didn't happen. Spark allows you to also customize how you do this caching, what this caching means. You could imagine that maybe you have a larger data set than you have available memory on a machine. So Spark gives you many different options for customizing kind of what happens in that scenario. You can specify that you want things cached only in memory ever. So of course the space used by Spark is a lot, yet things stay much faster because you have stuff sitting in memory. Remember this latency table that I showed you earlier in this lecture. So things are much faster because everything is in memory. If you remember from that same latency table, when things are written and read from disk, it takes a couple orders of magnitude longer to read and process this data. So for example, you can say everything should be cached to disk. So almost no space gets used in memory by Spark, yet it takes much longer because you're having to read and write from disk. And there are various mixtures of these two. Spark will spill data to disk if there's too much data to fit in the memory. And in this case, what we mean is that it spills to disk if there's too much data to fit in memory, but that serialized representation is stored in memory. So you have to serialize and deserialize, so you can save space in memory, but it takes a little bit longer because you have to do this serialization or deserialization step. So the representation for each object, for example, might be much smaller if you store it in serialized representation in memory, but as you can see, the CPU time increases. In Spark, the default, when you call persist, is this memory-only option. So the idea of keeping everything that you can stored in memory so that computation happens faster. At this point, I want you to also keep in mind that there exist other important transformations on RDDs, beyond the transformer-like combinators that you may be familiar with from Scala collection. There are a number of other important transformations that Spark introduces. One, for example, is the idea of sampling. So you can provide you can sample a fraction of the data without replacement, given a random number generator seed. So if you, instead of doing take 10, you can more accurately sample the data set that you have rather than taking the first 10. You can sample throughout the whole collection using this function. The union function will return a new data set that contains the union of the elements in the source data set and the argument. So we call it a pseudoset operation because it's not a set operation like you might have seen in Scala collections. Duplicates remain. And the same is true for this intersection method. So it returns a new RDD that contains the intersection of the elements in the source and dataset and the argument. And again, duplicates remain. It's a pseudoset operation. So distinct is another operation that you might be familiar with. It returns a new dataset that contains the distinct elements of the source dataset. That's not too surprising, but these other two operations, coalesce and repartition, these are more special, more related to Spark. Since we're doing these operations on distributed pieces of data spread all over different machines, you might put yourself in a situation where you filtered down a very large data set and you want to reduce the number of machines that you're using so that more stuff can happen in memory and you don't have to be sending data between nodes when there's only a few pieces of data on each node. Maybe you can combine everything onto one node. These two operations help you do that. So the coalesce method decreases the number of partitions in the RDD to some number of partitions that you specify, and it's useful, like I said, when running operations, keeping them running more efficiently by putting more stuff in memory on fewer machines after filtering down a large data set. Repartition is similar. The idea is to reshuffle the data in the RDD to randomly create either more or fewer partitions and balance across them. So you could end up in a situation where you have sort of a imbalanced partitions, where maybe on some machines you have more data and other machines you have less data. So you can do this reshuffling to make everything more balanced. But keep in mind that repartitioning causes this thing called shuffling, which means we're moving data all over the network. As you might recall, sending data around is expensive. So we always have to try and keep in mind when shuffling is happening. That could amount to enormous performance hits. So the last few RDD operations that I'm going to cover are some other important RDD actions. So the previous two slides were showing different RDD transformations that might not be one-to-one with the ones that you're familiar with from regular Scala collections. Here are the actions versions of these rather different operations on RDDs. One operation that you might find rather important when you start doing exercises with Spark is this collect operation. Collect, basically what it does is it returns all the elements of the dataset as an array to the driver program. So the idea here is that perhaps we filter down a dataset and we've come up with some result that's small enough to fit in the memory of one machine. And with that result, we can call collect on that result to get that back to the driver program and then do something with it. There's the count operation, which is a bit self-explanatory, and there's also the for each function. Now, this is an interesting function. So the idea here is to run a function, some specified function on each element of the data set. And this is usually done for side effects such as interacting with external storage systems. But this is also something to keep in mind. The return type is units, so this is all being executed on the cluster, but nothing ever comes back to the driver program when you call for each. So it's similar to for each in collections, regular Scala collections, but one has to remember this driver worker sort of topology when calling it. And finally, save as text file. So, and this is a bit self-explanatory. The idea is that we write the elements of the dataset as a text file or as a set of text files in a given directory in some local file system, or also in HDFS or some other Hadoop-supported file system. So Spark will call toString on each element to convert it into a line of text in the file. So it already does that work for you. Now, something that differs a little bit from Scala collections is this notion of a pair RDD. So pair RDDs are very important in Spark, and a lot of operations are done on pair RDDs. We usually like to think in terms of things like hash maps or sequences, stuff like this in Scala, but in Spark, there's this notion of a pair RDD. It's like a big collection of key value pairs. So it's useful because pair RDDs allow you to act on each key in parallel or regroup data across the network. It's a little bit different than how you think about hash maps. So in a distributed scenario, when you have all of your data organized into these key value pairs that are spread over the network, there are a number of specialized operations that you might want to do. So given some key, you might want to group on all things that have that key, or you might want to reduce on all things that have that key. And of course, there's joins, which you might be familiar with from the database world. All of these things exist on these things called pair RDDs. But one thing I really want to highlight is that operations on pair RDDs might require shuffling. Shuffling, as alluded to earlier, is moving the data around the network. This can be very expensive. So it's important to know what you're doing when you're using operations on pair RDDs. We'll cover pair RDDs more in the next lecture. However, my hope was just to give you a sampling of the sort of RDDs that we would normally be using when writing applications in Spark. We have this notion of transformers, of actions, and we have this notion of pair RDDs, which can sometimes be expensive depending on how you use them. So those are some of the basic concepts that I wanted to cover this week about Spark. Next week we'll look more at these pair RDD things, and we'll learn a little bit more about when shuffling happens and how to avoid it.